So good morning, students. Today we are moving towards our next unit, that is the WDM and the DWDM systems. So first of all, we have to talk about the multiplexing. So multiplexing is a process where the multiple analog message signals or the digital data streams are combined into one signal over a shared medium. Now the types of multiplexing, there are two types of multiplexing. The first one is the time division multiplexing and second one is the frequency division multiplexing. Now the type of optical multiplexing, that is a time division multiplexing, and WDM, which is a wavelength division multiplexing. So we are here to discuss the wavelength division multiplexing. So first of all, the concepts of the WDM and the DWDM. If we talk about a point-to-point link with a single fiber line, there is an optical source at the transmitting end and an optical detector at the receiving end. With such a scheme, if signals from the several optical sources are to be transmitted, each one would require a separate optical fiber. It is important to note at this point that the spectral sources for fiber optic communications, particularly laser diodes, have very narrow spectral bands. Such sources use only a very narrow portion of the available transmission bandwidth of optical fibers. For multi-channel operation, therefore, it is possible to operate each source at a different peak emission wavelength and achieve a simultaneous transmission of all the optical signals over the same single fiber. Now, this is the basic concepts involved in the WDM. So the wavelength division multiplexing, WDM, is a technology which multiplexes a number of optical carriers signals onto a single optical fiber by using different wavelength, that is colors of the laser light. This technique enables the bidirectional communication over one strand of the fiber. Now the problems associated in the communication technology is the demand for massive increase in the capacity. So the immediate solution is about the DWDM multiplexing. The long-term solution is about the optical fiber networks. So the WDM overview, here we can see the four ports A, B and XY. A and B wants to communicate with the X and Y. So we can see here that A and B are at the input end. The wavelengths are lambda 1 and lambda 2, and X and Y are at the output ends. So here we will apply a wavelength division multiplexer, and then we install here a fiber. So in the fiber we get both the wavelengths lambda 1 and lambda 2. Now at the receiver side we here have the wavelength division demultiplexer. Here in the above line we get the lambda 1 and lambda 2 in the below line. So at the X we get the lambda 1 and at the Y we get the lambda 2. The multiple channels of information carried over the same fiber, each using an individual wavelength. A communicates with X and B with Y as if a dedicated fiber is used for each signal. Typically one channel utilizes a 1320 nanometer and the other a 1550 nanometer. Broad channel spacing several hundred nanometer. Recently WDM has become known as coarse WDM or the CWDM to distinguish it from the DWDM. Now WDM overview, another example, suppose there are the three ports A, B and C and wants to communicate with X and Y and Z. So here the wavelength is lambda 1, lambda 2 and lambda 3. Here we apply the wavelength division multiplexer. So in the fiber we get lambda 1 plus lambda 2 plus lambda 3. So at the end of the wavelength division demultiplexer, we get the lambda 1 at the x, lambda 2 at the y, and lambda 3 at the z. The multiple channels of information carried over the same fiber, each using an individual wavelength. It is a attractive multiplexing techniques. The causes are it have the high aggregate bitrate without high speed electronics or the modulation. It has the low dispersion penalty for aggregate bitrate. It is very useful for the upgrades to installed fibers. It is realizable using commercial components unlike OTDM. It have the losses, crosstalk, and nonlinear effects in the WDM is a potential problem. So we use the DWDM, that is a dense wavelength division multiplexing system. So here you can see that we have a wavelength from lambda 1 to lambda n. Here we apply a wavelength division multiplexer, and here we apply a wavelength division demultiplexer. So at receiver side we get the lambda 1 up to lambda n. Suppose here is the transmitter. Suppose n number of transmitters, and here are the n number of receivers. Multiple channels of information carried over the same fiber, each using an individual wavelength. Unlike CWDM channels are much closer together. Transmitter T1 communicates with the receiver R1 as if connected by a dedicated fiber, as does the T2 and R2, and so on. Some key points regarding DWDM. The dense wavelength division multiplexing is WDM utilizing closely spaced channels. The channel spacing reduced to 1.6 nanometer and less. It is a cost-effective way of increasing capacity without replacing the fiber. The commercial systems available with the capacities of 32 channels and upward is greater than up to 80 GB per second per fiber. It allows new optical network topologies, for example, high-speed metropolitan rings. Optical amplifiers are also a key components of DWDM systems. Now the advantages of DWDM systems are it is the greater fiber capacity, the easier network expansion. It have the easier network expansion because no need of a new fiber needed. Just add a new wavelength. Incremental cost for a new channel is very low, and no need to replace many components such as optical amplifiers. Now this is a diagram of the DWDM system. Here you can see the transmitter, that is and here is a DWDM multiplexer. Here we apply the power amplifier to amplify the value of the signal, and here you can see the fiber, optical fiber, and again we apply here a line amplifier, then again the optical fiber, again a line amplifier, and again a optical fiber cable. So here the length of this portion is about 200 kilometer, and after that we apply the receiver pre-amplifier, and here we again apply the DWDM demultiplexer, and here you can receive the signal at the receiver end. So here each wavelength behave as if it has its own virtual fiber. Optical amplifiers are needed to overcome losses in the mux and demux and the long fiber spans. Now the DWDM typical components. So there are two types of the components in the DWDM systems. The first one is the passive components, and second one is the active components. In the passive components, the gain equalization filter for the fiber amplifiers, the brake rating based demultiplexer, array waveguide multiplexer or demultiplexer, then the add drop coupler, then active components or subsystems are the transceivers and the transponders, DFB, lasers at ITU specified wavelength, then DWDM flat, EDFA, erbium doped fiber amplifiers. This is the DWDM system with the airdrop components. Here a DWDM multiplexer, here the power amplifier, then optical amplifier, and here we apply the airdrop mux or demux. Then again here is the optical amplifier and line amplifier, and the previous discussed optical amplifier and a receiver pre-amplifier. And after that we again apply the DWDM demultiplexer, and here at the receiver end we get the receivers. So here we install the airdrop mux or demux. Here it is a length about the 200 kilometer. A wavelength such can be added and dropped as required at some intermediate location. So it is enough for now. Thank you so much.